Good morning. I hope everyone is ready for a little more thermodynamics. We're moving on to chapter 18. This is referred to as kinetic theory. It says kinetic theory of gases, but oh, here we go. And liquids and solids. Somebody added that. Thank you. So we're looking at kinetic theory now. Kinetic theory says that what we consider to be thermal energy, sometimes referred to as heat, and we'll see there's more specific definitions for those. But thermal energy actually is just the molecules in motion. It's the measure of how much energy, how much kinetic energy and potential energy a collection of molecules have. So that's referred to as kinetic theory, and back in the 1800s, that was just a remarkable suggestion or discovery that everything was, during the 1800s. I always think of kind of thermodynamics as being kind of physics of the 1800s, where they were discovering the existence of atoms and molecules and then making the connection between thermal energy and the kinetic energy of the individual molecules. So that's kind of what this chapter is looking at. So let's take a look and see what we've gotten ourselves into. So we're going to be looking at the usual set of topics. I did cross out a few of these. Mean free path, no. Diffusion, you guys don't have to do those. So we're going to have more than enough looking at the other topics we have listed here. Now, let's go back to the ideal gas law and think about what the ideal gas law may be telling us. So the assumptions of kinetic theory is that typically we have an enormous number of molecules. Now, if it's gases or liquids or solids, we typically have an enormous number of molecules. Now, for the gases, those are moving in random directions. The molecules are far apart on average. The molecules are following the formulas. I always have a problem with this when they say these particles are obeying the laws of physics. Anyway, maybe that's my own personal issue I have to work through. But I just want to say that these molecules are well represented by the formulas that we have developed. So there's a set of formulas we've developed from classical mechanics. What is kinetic energy? What is momentum? A kind of a list. What is angular momentum? And it turns out that these molecules, we'll find, we can understand them as being objects with some of the properties that we've talked about already in classical physics, chapters 1 through 16. And then we say that the molecules interact actually fairly infrequently. There's, for air molecules, for example, they're spaced quite a distance away from each other, and the collisions are going to be not that frequent. Now, the collisions, I guess we have to ask, what does that mean? The collisions, we assume, are perfectly elastic. So that means that molecules you can't have a hot molecule and a cold molecule. You can't hit a molecule and transfer thermal energy to an individual molecule. Thermal energy is the kinetic energies of the molecules. So one of the nice features of getting down with these individual molecular collisions is that the collisions are going to be typically elastic, meaning that the energy can be conserved. The energy is going to be accounted for in these collisions. We'll have to be more clear and specific about those statements too. Anyway, here's a pretty good derivation of the ideal gas law based on mechanics, based on chapters 1 through 16. So I'm going to go through this pretty quickly. It's not essential that you follow all the steps. If you want to see how this develops, I think that's great. If not, that's not a problem either. But here is a box with a container with a bunch of gas molecules inside. Now, back in the earlier part of this course, we found that the force could be calculated as a momentum transfer divided by the time interval. It was momentum per time to calculate how much force. And what we're interested in is how much force is there acting on one side of the container. Now, one side of the container is actually representing more than just one side of the container. It's representing any location on the outside of the container, and it's representing any location within the container. If I put something in the container, how much pressure would it experience? We're headed towards that calculation. So for right now, we're going to let this side of the container keep track of the force that we're calculating. Now, if I look at one molecule at a time, I can look at how its momentum changes when it collides. Now, if the molecule collides with a wall, the wall is fixed, and energy conservation says the molecule will bounce off with the same energy it went in. The collision will be elastic. And that says that the momentum will be 2mv, but wait a minute, the molecules have Vx, Vy, and Vz components. So the force, or the momentum, if I have a molecule come in, hit the wall, bounce off, there's really only one component of momentum, of velocity, that gets reversed. So we'll say 2mvx, and the time interval depends on the distance that it has to travel. Now, the molecule bounces from side to side, but we're only keeping track of this wall. So that means in terms of x displacement, it will have traveled L and then L again. It travels in the x direction exclusively, a distance of L and then a second distance of L. So that's two distances of L divided by the velocity again only in the x direction. So notice we're just solving for one wall right now, and we're only solving for the direction of motion, the x direction, where the molecule will impact that wall. So that gives us the force is mv squared over L. That's the average force of one molecule bouncing around inside the container. So it's the force of the molecule on just one wall. Now, what happens when we put all the molecules in there? Well, then the force will be equal to mv squared over L for each molecule. Now, the different molecules are going to have different values of Vx. They're not all going to be the same. And that tells us that I have to introduce the average value. Now, that's not the average value of V, it's the average value of V squared. So I have to add up all the V squareds for each molecule, average them, and then multiply that by the number of molecules, and that will tell me the force of n molecules, all bouncing around randomly. How much force are all the molecules together creating along that wall? Now that's a sustained force. That's not a force of one impact. That is saying every time interval, each molecule hits that wall. And the time intervals are different depending on how the molecules are oriented, but we've taken that into account. So we've taken that into account by only looking at the x velocities. So that's kind of interesting. That is the sustained force along one wall due to the presence of n molecules inside, all with different velocities. Now we've got to find some way to figure out what those velocities are, but we can do that. We'll get to that. So here we go, same box. Each molecule is going to have a Vx and a Vy and a Vz, and those could be different. Now the combined velocity of each molecule is Vx squared plus Vy squared plus Vz squared square root. So each molecule will have its own value in general of Vx, Vy, and Vz. So that says the average value of V squared, the average value is the bar over the top, and then the average is equal to the average value of Vx squared plus Vy squared plus Vz squared. Now, by symmetry, if I look at all these molecules, the average speed in the three different directions are going to match on average. Some molecules will have higher velocities in the x, not so much in the y and z. Some molecules will have more of their velocity in the y, some molecules will have more of their velocity in the z. But on average, these values will match for the entire collection. So that says I can take the Vx squared, which we introduced, and say that is 1/3 of the combined V squared average. And that's what we want. We want to know the total average, not just one of the components. Well, this is what we put together on the previous page, that the force of one molecule on one wall will be a sustained average force of mv v sub x squared over L. Now the gas molecules, it turns out, are moving really fast. We're going to find out that air molecules at room temperature are moving about 500 meters per second. So it's moving back and forth fast. Now I realize there's only a force when it impacts the wall, but we can average over the impacts because there are going to be so many air molecules and they're all going to be hitting pretty frequently. So each one on average then, I can take the Vx squared and replace it with 1/3 V average squared. So that's the average force of an individual molecule, and then I can multiply by n. So if I multiply by n, now it's the entire collection. And then what I can do is I am going to convert over into kinetic energy. So mv squared average can be written as 2 times the average kinetic energy. So the idea is to not solve the formula in terms of average velocities, but instead solve the formula in terms of average kinetic energies. All right? Now, we're interested not so much in force, but in pressure. How much pressure is that force creating? And pressure is force per area. So if the pressure is force per area, that would be force divided by L squared. That would be this formula divided by L squared. That gives me L to the 3rd power. L to the 3rd power, that's the volume. All right? So, so I now have a pressure formula that says this. It says that the pressure inside this container, and now I don't have to think about it being one wall. I've solved for the pressure. Whatever pressure I solve for that one wall applies to every location within the container. So the pressure inside the container is given by 1/3. The 3 is there because of the 3 dimensions of space, x, y, and z. It's proportional to the number of molecules. That seems like it makes sense. It's inversely proportional to the volume. If the volume spreads out, the molecules are more spread out and I'll have less pressure. The number of impacts will drop. That seems okay. And then it's 2 times the average kinetic energy, and that's because that's the formula that says how the kinetic energy is related to mass and velocity. All right, so we're getting to something that looks a bit like the ideal gas law. So let's tidy things up a bit. We'll say that the pressure is equal to 2/3 times the number of molecules times the average kinetic energy over the volume. Now, it's repeated right here. Well, not quite. Pressure times volume. So now we've got the left side of the ideal gas equation is equal to 2/3 n times the average kinetic energy. Now, the average kinetic energy then, let's do this first, I guess. So now we're going to bring in the ideal gas law and say that the ideal gas law says pressure volume is equal to nkt, where n is going to be determined experimentally. And we've observed this is how gases behave. And now we can make the connection. We can say that the average, 2/3 times the average kinetic energy is equal to Boltzmann's constant times the temperature. Solving for average kinetic energy, it's 3/2 kT. All right. So So for physicists, that's a big deal. That's really important to us. What we've actually been able to do is use classical physics, the kind of stuff we learned in chapters 1 through 16, and we're assuming the existence of atoms and molecules. And what we've done is gone through and derived what the kinetic energy for a molecule will be on average at a given temperature. Now again, Boltzmann's constant can be experimentally determined, and so we can run a bunch of experiments and determine how much kinetic energy, calculate how much kinetic energy these molecules will have on average. All right. Now, once we get the average kinetic energy, we can find out how fast they're traveling. So this is going to open up a lot of possibilities. We can go in and list some of these properties of gas molecules. So I think these are part of the derivation we just did, so I'm not going to worry so much about going back over these. And rewriting, there we go. So this is their version of deriving the very same formulas, the same ones we just did. The average kinetic energy is 3/2 kT, or equal to, here we go, the average kinetic energy is 1/2 m v squared average. Now remember, that's not v average squared, it's v squared average. So we got to square first and then average those numbers. But that's going to allow us to go in and calculate the velocity of gas molecules on average as a function of temperature. So that's pretty cool too. And just for emphasis, they have a period. So the average translational kinetic energy of a molecule in an ideal gas, which basically says in almost any gas that we look at, is directly proportional to the temperature. So the average kinetic energy rises proportional to the absolute temperature, which has got to be in kelvins for this to work. Now, yeah, and then this is only translational. This is not rotational energy yet. We have not looked at rotation. This is not vibrational. It's exclusively translational energy, what we talked about back in, I want to say, chapters 10 and 11. Okay, molecular kinetic energies, here we go. What's the average translational kinetic energy of a molecule in a gas at 37 Celsius? So there is a temperature. They're trying to fool us. They're trying to give us Celsius. We're not going to fall for that. We're going to immediately, right there, immediately convert from Celsius over into kelvins. There we go. Now, the average translational kinetic energy, this is only translational, we should get that written in, 3/2 kT. And Boltzmann's constant, just a reminder, 1.38, 10 to the minus 23 joules per Kelvin. Now, see, what do we have here? So the average kinetic energy, I guess we're done. 3/2 kT, oh yeah, we're done. We just plugged all the numbers in. I was thinking we did that in a series of steps, but we didn't. We just plugged into that formula, and it says that the average kinetic energy of each one of these molecules is 6.42 10 to the minus 21. Now it varies. We've said that, we've mentioned that a couple times. If I take a collection of gas molecules at any instant, some will have more than average kinetic energy, some will have less than average, and as they have collisions, that kinetic energy gets transferred back and forth. Now there is a distribution that we can demonstrate, a pretty well-defined distribution of how the kinetic energies are distributed at any particular instant in time. Now, what gases would this apply to? Well, any of these, helium, neon, argon, those are all monatomic. Those gases consist of individual atoms. There's nitrogen, oxygen, carbon monoxide, everybody's favorite gas. Those are diatomic. Those consist of two atoms combined to form individual molecules. And then there's things like carbon dioxide and methane, where you are polyatomic, you've got 3 or more atoms combining to form the molecule. All right, this is kind of fun. Now, the internal energy of the sample. So, what would that be? Okay, if I take all the kinetic energies of all the molecules and I add them together, what I'm going to get is n times the average kinetic energy. And we call that the internal energy for the sample. So the internal energy can be calculated. Oh, it was right here the whole time. The internal energy of the entire sample can be determined by taking the average value per molecule and just multiplying by the number of molecules. If I add all their energies together, some will be lower than average, some will be higher, but by the time I've added them all together, the total internal energy will be n times the average. Now the average kinetic energy we determined to be 3/2 little k times t, and that says the internal energy of translation, this is only translation right now, is 3/2 nkt. So 3/2 times the number of molecules times kt, that can also be written as 3/2 PV, because we know from the ideal gas formula that nkt is equal to P times V. So how do we find out what the internal energy is of a collection of gas molecules? Well, we have 2 options. We can say what temperature is it and how many gas molecules are there, or we could measure the volume and measure the pressure. Measuring the volume and measuring the pressure will enable us to determine what the total translational kinetic energy is for the entire collection of molecules. Now, I went in and calculated a couple other items here. I'm always curious how many molecules are there, and so I put in, I shouldn't have used 100,000. Why did I use 100,000? That's just a bit of an estimate. So I used a volume of 1 cubic meter, and I used a pressure just a little less than 1 atmosphere, but pretty close. I put in 100,000 pascals just to make the calculation a little faster, I guess, and 1 cubic meter. Now, if I put those numbers in and use them, what I can do is calculate how many molecules are in my sample, and that works out to be 2.34, 10 to the 25th number of molecules. How much would the internal energy be? And if I take that number of molecules and multiply by the average kinetic energy, so this is the number of molecules, average kinetic energy, look, it's 150,000 joules. So now I could have also done this by taking 3/2 times P times V. So 3/2 times P times V is giving me 150,000 joules. In any case, that's 37 Celsius though. Okay, so this is at 37 Celsius, it's at a fairly high temperature. At that high temperature we'll have fewer molecules, but again, what I've got is a cubic meter of air, and the pressure is roughly 1 atmosphere, and the translational energy is 150,000 joules. That's a lot of energy in the air molecules within a cubic meter in the room. So the total translational kinetic energy, cubic meter by cubic meter, is going to be 150,000 joules if we're at a pressure around 1 atmosphere. Okay, so now let's go in and see if we can figure out how fast these molecules are traveling. So that would be really interesting to find out, I think. So we can now calculate the average speed of the molecules as a function of temperature. Now what we introduce is a little funny, but there's a reason for it. We introduce what's called the root mean square velocity. Now we refer to this as RMS. And RMS averaging shows up, from time to time. At some frequency, we run into RMS averaging. RMS averaging gets used when we have something where we want to average the square. So we'll see it, a few times during during this course, and during Physics 3B it will show up again. What VRMS says is we take each molecule and we write down the value of V, and then we square it. After squaring it, we add them all together and divide through by the number of molecules. That would be an average of V squared, and then once we get that done, we take a square root. Now the reason we do that is if I square the velocities, I'm not in velocity units anymore, I'm in velocity squared units. What we want is an average that tells us something about the velocity itself. And so that's why at the end of this, we take a square root. Now I always feel like they got the name backwards because the order of operation here is, first of all, I square everything, and then I take the mean, that's an average, and then I take a square root. But I think what they mean is the square root of the mean of the squares. Yeah, that's it. So square root of the mean of the squares. And that's what that formula looks like. Now, how do we use this? Let's look at speeds of air molecules. What is the RMS velocity of oxygen and nitrogen at 20 Celsius? So here we go. Now, here is the formula that we derived. It says the VRMS, kind of the average speed, is 3 kT over the mass of a molecule square rooted. Well, that's a little hard to do. First of all, Boltzmann's constant has all that scientific notation. Okay, that's not such a big deal. But the mass in this formula is the mass of an individual molecule. That's hard to do. So what we can do instead, and what I highly encourage, is if you don't want to have to go in and solve for the mass of individual molecules, what you can do is multiply top and bottom by Avogadro's number. If I multiply Boltzmann's constant by Avogadro's number, I get big R. If I multiply the mass of one molecule, I get the molar mass. Those are going to be easier. So I'm going to use the formula on the right. Now, even with that said, there's still a couple of pitfalls we have to watch out for. And here they are. First of all, I still need to get the temperature in kelvins. Because Celsius 0 doesn't really mean 0. Kelvins it does. Kelvin means what it says. The nitrogen molar mass is 14 grams per mole. The oxygen molar mass is 16 grams per mole. And those are coming off the periodic table. So those are very prominent isotopes. Almost 100% of the nitrogen is the 14 isotope. The oxygen isotope, the prominent isotope is 16. So that says that O2, the oxygen in the air, has a molar mass of 32 grams per mole. That's got to be converted into standard units, and you might say, well, wait, what's wrong with grams per mole? It's not kilograms. So we're depending on using joules for energy units, and joules have kilograms in them. Grams aren't gonna work. So I have to take my molar masses and convert them into kilograms per mole, which is 0.032. Now I plug them in the formula. 3R absolute temperature, molar mass. How did we do? The K's, the kelvins cancel, the moles cancel. I have joules per Kelvin. When I take the joules and divide by, kilograms, the kilograms in the joules go away, and the kilograms go away, and I have meters squared divided by seconds squared. And then I take a square root. Hey, it worked. Check them out. Again, you should be going through every example that we look at. Check the units on this, check the calculations. I got 478 meters per second for the average, for the VRMS for oxygen molecules. Now, for nitrogen, what we know is that the energy gets divided up on average equally. So if I give nitrogen the same amount of energy, it's lighter. It's only 0.028 kilograms per mole. And carrying out this calculation, which looks identical, it's going faster. It's going at 511 meters per second. All right. Now, these are translational energies, and those are given by 3/2 kT, and that is 6.07, 10 to the minus 21 joules. That's the average kinetic energy of all the molecules. O2s, N2s, argon, H2O, CO2. The average translation of each one at translational energy at 293 kelvins is 6.07, 10 to the minus 21 joules. All right. Okay. Any questions? Stop by. This is fun stuff to talk about, I think. All right, we have a tank of helium in this example, and the tank of helium is being used to fill balloons. As each balloon is filled, the number of helium atoms in the tank decreases. Yeah, that's kind of expected. How does this affect the RMS velocity of the molecules? Ooh, we got to think about this one. Okay, we got a collection of gas molecules, and we're taking the gas molecules out. The helium originally is at a really high pressure, but it drops to a lower and lower pressure. How is that going to affect the speeds of the molecules? And if the helium is staying at the same temperature, then the VRMS values will be the same. What that formula told us, the formula that we derived and worked with, said that it just depends on temperature. Let's take a look. So the VRMS values are just going to depend on temperature and molar mass. If all the helium atoms, well, all the helium atoms have the same mass, at least all the isotope 4 helium atoms, and so the speed should stay the same if the temperature is staying the same. So, and that becomes a question. If the temperature is staying the same, but I am assuming it is from what they're telling us. All right, let's do this. Let's calculate an average speed and an RMS average speed and see what the difference is. So we've got 8 molecules, and these are just some made-up numbers. They have speeds of 1, 6, 4, 2, 6, 3, 2. And these are being measured in meters per second. These molecules are really slow. Haven't they seen the speeds of real molecules? Like, they're really fast. So find the average value of those numbers, and then find the RMS. Okay, now the average doesn't sound too difficult. So let's try this. Average speed versus RMS. Here's the average. 1, 6, 4, 2, 6, 3, 2, 5. I added them together. I divided through by 8. This is the formula for averaging. 1/8 of 29, which is what they added up to, gives me 3.63 meters per second. Done. All right, the average wasn't so hard. What about the VRMS? Well, we said the first step was to square everything. So I'm going to take the 1 and square it. 6 squared, 4 squared, 2 squared, 6 squared, 3 squared, 2 squared, 5 squared. I'm going to add all the squares together. That's 131. And then what I have to do is I have to take the 131 and divide through by the 8 molecules. And that says on average, the V squared value for the molecules is 16.4. Now you might think that I can take the average and square it and get the square of the average, the average of the squares, but that would be mistaken. That's not true. The operations are not, they don't commute. They're not interchangeable. I have to do the squaring first, and then doing the averaging, and I'm going to get a different number. And it's going to be bigger than squaring the average consistently. All right, now we're not to RMS yet, because the units we have are not back in velocity units yet. So what I'm going to do is take a square root of that number, and it becomes 4.07 meters per second. Okay, so the VRMSs are always going to be higher than the average velocities. But the VRMSs are more directly related to kinetic energies. So the conversion between VRMS and average kinetic energy is just 1/2 m VRMS squared. And that's what we have here. So this is a more direct relationship with the kinetic energy, average kinetic energy of the molecules. Okay, molecules in a gas are not all going to have the same velocities. We've been saying that, a few times. And now what we're looking at is a scary, scary function that says this function is telling us how many molecules in a sample will there be that have a particular speed. So it's the number of molecules on the vertical axis, number of molecules per speed as a function of speed. And there's a lot of stuff going on, and we're not going to look at all the details. What we are interested in is there's a couple effects going on here. First of all, there is a v-squared effect. Now the v-squared effect suggests that as you go to higher velocity, there will be more molecules at higher velocity. And initially, that's what happens. What we find is that the number of molecules just at sitting still is basically 0. Now that might seem surprising, but we'll show why that's going to happen. It's very, very unlikely. Statistically, we can just go in and show, very unlikely for a molecule to be traveling with no velocity at all. Or rather, for a molecule to be at rest, let's say. As we start to increase velocities, we start to see the v-squared effect. So it appears that there's more ways of going fast than there are going slow, and that's true. So as you go to higher and higher speeds, there's actually many more ways to go fast than there is to go slow. It's kind of a funny statement, but we'll see why that is. But then something happens. So as we start to go to higher and higher velocities, the molecules go, wait a minute, we can't go to everybody to high speed. There's only so much energy to go around. So there's an energy limit, and that's what the exponential drop-off is telling us. As we go to higher and higher energies, 1/2 mv squared is the kinetic energy. As we go to higher and higher energies, the probability that an individual molecule will acquire that much energy begins to drop off. There's a limited amount of energy to go around, and so what happens is, at first we see the v-squared effect, but then eventually the exponential drop-off takes over, and reality sets in, and we go, no, we don't have enough energy for everybody to go super, super fast, and that's what the distribution looks like. Now, it's kind of remarkable, I think, that we can derive this formula, we can go and experimentally verify this, and as the molecules undergo all these random collisions, they still maintain this distribution. And that's because there are so many of these molecules that the statistical fluctuations are small. So any sample of gas molecules at thermal equilibrium will have this distribution of velocity, something very close to this distribution. Now, there's a couple of averages in this graph. There's an averaging technique here, which is called, well, they're calling it the peak velocity. That is the velocity at which the probability function peaks. You know, which velocity is more probable than any of the other velocities. And that's it. Now the average velocity, which we looked at in the previous example, is a little bit beyond that. And that's because the tail on this side goes on and on for a long distance. But on this side, there is a sharp cutoff at 0. Okay, so the average velocity is shifted a little higher, and then the VRMS is shifted even higher, and that's because we're squaring the velocities. We're giving extra emphasis to the molecules that are moving the fastest. We're giving them an extra boosted effect. Okay, here is a collection of gas molecules. Again, individual gas molecules will have velocity in the x, velocity in the y, velocity in the z, that will combine to be an overall velocity. Now, we could take these gas molecules out one by one. Well, we can't do this, but we could imagine doing this. So let's imagine taking the gas molecules out one by one and measuring their Vx, their Vy, and their Vz. And then what we're going to do is we're going to plot that information on this three-dimensional graph. So this three-dimensional graph has perpendicular axes of Vx, Vy, and Vz. And when we measure this, you know, here's a molecule that's mostly Vz, not so much Vx and Vy. Here's something that has a lot of Vx and Vz and Vy. Here's a molecule that doesn't have much of any of it. Anyway, we can plot them all. What nature tells us is that, statistically speaking, if energy were not an issue, if we didn't have to worry about the limited amount of energy available to these molecules, then any location on that graph would be equally likely. They could be traveling with any speed they want, any combination of Vx, Vy, and Vz. Now notice, when we combine the individual components to get the total speed, this formula is the formula of a sphere. So we can identify a series of spherical shells, and all of the points along that spherical shell represent gas molecules that have the same speed, but a different collection of individual components. So if we say the point right at the middle of the graph corresponds to being completely at rest. The point right at the middle is Vx equals 0, Vy equals 0, Vz equals 0. How many ways could that happen? One. How many other possibilities are there? Like an infinite number. And so the probability of being at rest is basically 0. Now, as we come out to higher speeds, the surface area of that shell corresponds to the probability of traveling at that speed. And as we go to higher and higher speeds, the size of the spherical shells get bigger. So as we go to higher and higher speeds, there are more ways that the Vx and Vy and Vs can combine to provide that particular speed. So bottom line, there's more ways to go fast. Now, this is factor number 1, and it actually comes from quantum physics. Quantum physics tells us, when we go in and analyze this quantum mechanically, that each location in the graph, in some sense, is equally likely. That's the first factor. But then factor 2 steps in and says, wait a minute, there's only so much energy. There's not an infinite amount, so that's going to provide a cutoff. If there was no limit to energy, then these would be just randomly placed anywhere in terms of their velocities. So that becomes an exponential cutoff, and that gives us the distribution that we observe. So the distribution we observe is the combined effect of those two factors. Factor 1, there's more ways to go fast than there are to go slow. Factor 2, there's only so much energy to go around. And that gives us what we call the Maxwell or the Maxwell-Boltzmann distribution of molecular speeds. Now notice, everything we looked at with these distributions only depended on the absolute temperature. So for the gases, for these ideal gases, we don't have to know the pressure. We don't have to know the volume. If we know the temperature of the sample, that's enough to construct the graph that we have. So it specifically depends on that. Now what happens as the temperature goes up? Well, the way this graph is defined, the area under the curve is proportional, well, the area under the curve equals the number of molecules. If we go back and look at this function right here, this scary one, there's a factor of n in here, and when we integrate over the entire distribution, everything else cancels out, and all we're left with is a factor, is n. So the area under that curve, when we integrate across all possible velocities, is just n, the number of molecules. And so what happens is if we go to higher temperature, something's got to give. When we go to higher temperature, the function flattens out. So I start to have more molecules at higher speeds, but I have fewer molecules at the lower speeds. And the average velocities go up. So the average velocities go up. The entire curve shifts to the right when we look at this. All right, here is, we'll see about this problem. We'll see if we want to do this. It says determine the average velocity and the peak velocities, formulas for those. And let's take a look and see what they look like. Again, they switch back to Greek letters. Don't do that. Stick with V. Don't switch over to new. Here we go. Okay, there's the scary formula. So here is this really scary formula. And these are a bunch of constants. We're going to say this is just something we call normalization to make sure when we integrate, everything just becomes n. This is the energy limitation factor, and this is the number of quantum states factor. This is the surface area of a sphere, 4 pi v squared. So those represent the spherical shells of the different velocity combinations. Now this is a function. They're saying it's a function of velocity, it's a probability. The number of molecules within one of the bins, one of the vertical bins, the number of molecules is equal to that function times dv, where dv is the width of that function. So these are kind of the basics of integration, and I'm hoping all of you should have taken Math 3A, and I'm hoping in your Math 3A class they got through the integration portion. I know they only do a couple chapters on integration in 3A, but these are kind of the basics. And you know, sometimes it happens that in physics courses you end up introducing kind of new ideas in the math that maybe weren't done in some of the math classes, and that's okay too. So we'll provide support. And at the end of the day, the stuff we're talking about here right now is to help you guys build a strong conceptual understanding of what's going on. So if you look at the homework problems, you won't see homework problems requiring you to carry out these integrations. So I'm thinking right now too, this might be a good time to take a break and recover from looking at this. So let's go ahead and do it. Let's go ahead and take a break right there, and then we'll come back and look at this some more and talk about it a little bit more.